All right, let's, in this video I want to go over Coulomb's law. Coulomb's law is a pretty simple concept. Honestly, you'll find that this resembles the gravity equation that we learned from Newton. We have a constant. In this case, it's our electrical constant. Okay, sometimes you'll see it as a K or just a KE. And then we have a charge and another charge, and it's divided inversely by the square of the distance between the two object centers. In this case, let's just remind ourselves what gravity's equation looked like. We obviously are going to get a different constant. So we have a G instead of the K. But really, the foundation is that I'm separated by some distance between two objects, and the objects are interacting. And that's kind of the beauty of this equation is all the inverse square relationships that we learned when we talked about gravity apply in this situation. And so that's kind of nice. Let's write out what our K constant is. That's going to be 8.9875 times 10 to the 9th power. And our units are Newton meters squared per Coulomb squared. Coulomb being a capital C on our units. And really, it just comes down to, can we put this into our calculator correctly? And can we just make sure we don't make simple mistakes? So let's say, for example, we have, this is a problem we did just in class. We have two charges, each with 2 coulombs of charge. And we'll say that they're at 1 centimeter apart. Okay, so that's my charge. This is my distance. So if I drop this into my equation, I get 8.9875 times 10 to the 9th Newton meters squared per Coulomb squared times by 2 Coulomb times by another 2 coulombs, because they're both that. Now, first mistake that people make here is they'll just put 1 squared. That's incorrect. Because this is centimeters. We need this to be in meters, which that converts to 0.01 meters. So 0.01 meters squared. Notice my units here. That squared is also here on the meters, so that cancels with that meters squared. And then I have Coulomb squared down here. That's going to be on my denominator, and a C times C. It's going to give me C squared on top. With me with just newtons is my final unit. And that's a good indicator that I'm on the right track, that my units work out. The final step really is just quite simple. You just plug it in. Let's show you, make sure you plug it in correctly. We get 8.9875 times 10 to the 9th power, okay, times by 2, times by 2. Now I tend to do it that way first, get an answer, and then do divide 0.01 squared, like that. Notice I do it this way with the parentheses, the double parentheses, so that the squared isn't applied to the entire thing, it's just applied to the denominator. And there's my answer, and that's a ridiculously large number, but you know, for an example, it works. All right, another common question I might ask you is, what is the charge? So let's say, let's do an example of this. Let's say I have something simple. Let's say that my 2-point charges, so I got 2 charges, and there's a distance here of 1 millimeter, so they're quite close to each other, and there's a 20 Newton force acting between them. Okay, and I just want to know what is Q. Let's assume that they're the same size. Okay. Both of these, we'll just put that as QQ. Now, if we're doing this, and this is my equation, like that, since Q's are the same, we can just combine those. We didn't do this very often in gravity, like when we went over gravity, because most of the time we were comparing the mass of a planet with something, or the mass of a moon or a star. But it's not super uncommon to get two charges that are similar in size. And so in this case, we can just combine the Q1 and Q2 into Q squared. From that point, solving for Q is quite easy. I take this R squared, I'm going to times it to the other side. I'm going to get Fe times by R squared. And then I'm going to divide the K over. And then to finish things off, I'm going to do the square root to get rid of that squared there. And then from that point on, once again, the difficult part of doing this kind of problem is just make sure you put in your calculator correctly. Let's write it out so we have something to go off of. My force here is 20 newtons. Okay, my R squared is going to be 0.001 squared in the meters. And then, because once again, millimeters need to be in meters, so I have to do that conversion. And then I divide by 8.9875 times 10 to the 9th Newton meters squared per Coulomb squared. Now, some people may be thinking, wait, how did the units work on this? Newtons cancel, meters squared cancel, and I'm left with Coulomb squared. We're looking for a charge. And the charge is squared, but due to the square root here, the square root gets rid of the squared, leaving me with just coulombs as my final units. If I plug this into my calculator, let's see, 20 times 0.001 squared. Oops. Okay, 2 times 10 to the negative 5th. I'm going to do divided by, and then I'm going to put this whole thing in parentheses. Okay, get an answer, and then I'm going to do the square root of that. And then I'm done. 4.717 times 10 to the negative 8 coulombs. All right, so that works. Let's review really fast inverse square law relationships. Let's say that I have two charges here at some distance. Doesn't really matter whatever this distance is. And let's say there's a 20 Newton force between it, just like that last one. And let's say I quadruple the distance. Okay, so I extend this by 4 times. All right, and I just want to know, how does my 20 newtons change? Well, we're just going to do 1 divided by the distance, how it changed, squared. Okay, so 1 divided by 4 squared in this case, that's going to become 1/16 the original value. And so I'm going to take that 1/16, I'm just going to go 20 times 1/16 the original force. And 1.25 is the value in newtons. Okay, let's say, though, let's just change it up and say that I'm going to do it this way. I'm going to shrink it, okay, to be 1/4 the original distance. In that case, I would do 1 divided by 1/4 squared. In that case, that would become 16 times greater. And so I would do 20 times 16. Okay, and that would give me a value of 3,200. Or sorry, 320. Okay, so that would be 320 newtons. So that's just a quick reminder on inverse square relationships, just like what we did with gravity. But this is the important equation right here. Make sure you get this in your notes. Hopefully that helps you. If you have any questions, please come in and see me. Just let me know when you're coming in so I make sure I'm here and I don't have a meeting or something.